So we're going to take a little bit of a break from my weird patternings with our electrophilic addition reactions. It's a very small break, just for the record. And we'll look at some redox reactions, okay, or addressing reduction and oxidation. If you remember from Gen Chem, reduction was gain of electrons, which you should be remembering as Leo. Don't even get me started about oil. And then oxidation is loss of electrons is Gur, so Leo says Gur. And again, oil rig, you should just leave. That's just dumb. Leo says Gur is the way to do it. So, given this equation, we could now go through and determine what was happening within the individual reaction. We could say that the tin went from a +2 to a +4, and so it therefore had to lose electrons and was oxidized. Okay, so we had to, close enough. And that the iron went from an iron +3 to an iron +2, so it gained electrons and was therefore reduced. And we could go through and call these the oxidizing agent. Remember that they're inverted with each other. And the reducing agent. And to be able to determine all of this, we had to go through and look at oxidation states and all that fun stuff and loss of electrons. So because that's in reference to chemical reactions, we would fully expect to be able to have to do that for ochem as well. And herein lies the problem. Right away, you're going to encounter an issue because you don't have the same ability to determine oxidation states that you had in Gen Chem. In Gen Chem, we made a couple big assumptions. One, we were dealing with formulas, which made it easier to see how many carbons, how many hydrogens. But then we also had another big assumption, and that big assumption was that we had the same oxidation state for every single atom of that same type or that same element in a compound. And when we're looking at this particular reaction, this carbon has a different oxidation state than these ones, which is going to make it a little bit more difficult to go through and determine reduction and oxidation. Okay? The other big tweak that we go through in ochem that we want to address is that we kind of simplify things. I don't really care that this is a reduction and oxidation. I care about what happens to the organic compound. The organic compound has done a reaction. What happened to the organic compound? I know the sister or brother, depending on how you want to reference it, partner of our reduction and oxidation would also have to happen, but I don't really care. I care more what happened to the organic compound. So in looking at this one, maybe you remember something from Gen Chem, and that we have a loss, or an increase in hydrogen bonds. And an increase in hydrogen is equal to a reduction. Okay? If you weren't taught that, that's okay, because it's typically not taught. Okay? What might be taught would be a slightly different example reaction. What if we'd gone through and we'd started with, we can go really simple, CH4 reacted this with oxygen to produce CO2 and H2O. What happened to our organic compound? Okay, well, the carbon has increased in oxygen bonds. Well, an increase in oxygen bonds is oxidation. That's actually where the term oxidation comes from. It's in reference to the increase in the presence of oxygen. Okay, so those observations can help us interpret a chemical equation as reduction and oxidation easier than having to deal with oxidation states. Okay, so organic chemistry wants to simplify these rules. They aren't wrong, okay, but they aren't as useful for us because we're looking at these structures and we have to be able to determine oxidation states and reduction and oxidation faster than if we had to determine oxidation states. So the modified rules that we're getting is that a reduction is going to be an increase in hydrogen bonds. Well, sometimes you don't see the hydrogens, so a reduction is also going to be noted with a decrease in oxygen bonds. Okay, and we're going to tweak that in a second. The oxidation is an increase in oxygen bonds or a decrease in hydrogen bonds. Okay, so in the combustion example with CH4, we decreased the bonds to hydrogen to add in bonds to oxygen. So when we're going through and doing this, this definition works quite well, actually. But the oxygen becomes a bit tricky. Okay, so we're actually going to remove oxygen, and we're not going to reference it as oxygen anymore, and instead what we're going to reference that as is a more electronegative element. Because that's really what oxygen is. Okay, and the whole point of this is that we need a more electronegative element is being added into the structure, which is causing the electrons to be removed from our carbon. And again, our focus is on our carbons. So what we're doing in our process is really thinking about what changes and keeping our focus on that change around our carbons. Okay? And yes, we're going to look at some examples here in a second. If our rule of thumb does not work, then we can go through and actually determine oxidation states. Okay? The fun thing about that statement is the rule of thumb works. So we don't really have to determine oxidation states. But if for whatever reason you were forced to determine an oxidation state, the reference is homolytic cleavage minus heterolytic equals your oxidation state. So what do we mean by that? Well, if we look at each of these bonds, and we're going to pick methane, those bonds all have 4 electrons in them. If we're saying homolytic cleavage means the electrons in those bonds go back to their parent atom. So when we went through to make this bond, the hydrogens each contributed an electron into this. So if we were to do homolytic, and again, we have to pick our atom that we're concerned about. It's organic, so we'll pick the carbon. Homolytic cleavage says that I have 4 electrons around the carbon. Now, heterolytic, how many electrons would be around the carbon? Well, to decide that, we have to evaluate a difference in electronegativity. Carbon is more electronegative than hydrogen, not by much, but it is. Okay? Since it is more electronegative, what can happen is it's going to take all of the electrons, and we're going to get 4 minus 8 equals a negative 4. Okay? So the oxidation state for carbon in that structure is a negative 4. To give us a little bit of a check here, we have fully saturated with that with hydrogens. We can't add any more hydrogens, which means that is the fully reduced carbon. Okay, so our oxidation state should be as reduced as it possibly can be. Well, minus 4, that's pretty dang small. We're not going to be able to get smaller than a minus 4, so that is fully reduced. So let's take a look at the fully oxidized. Again, if we color code our electrons in those bonds, that can help us evaluate this. Okay, the homolytic cleavage again says 4. Okay, and now heterolytic cleavage. How many electrons does the carbon get to take? Well, it's connected to oxygens. Oxygens are more electronegative than the carbon, which means the carbon doesn't get to take any electrons. So 4 minus 0, and I would get a plus 4. Okay, the oxidation state for carbon in its fully oxidized system is a plus 4. If we went through to a plus 4 to a minus 4, we've now done a reduction. Everything matches, okay, with both our counting of our electronegative elements or our counting of hydrogens. So that can help us go through and evaluate and differentiate reduction and oxidation relatively quickly. We can do it with determining oxidation states, or we can do it by just looking at those rules that we summarized on the previous slide. To give you a little bit of practice with this, when I advance the slide here, we've got a bunch of practice outlined here. I would highly recommend that you pause the video, hit space, click the screen, stop it, try and answer these as either reduction and oxidation or neither, and then we'll go through and talk through them here in a second. So I added a new reaction, which is a carryover from our past slide, And I also added the definitions as kind of a subtle thing on the left. Oxidation is an increase in electronegative elements, and reduction is an increase in hydrogen. So we've got all the answers written on here, but it might be helpful to go through and do some labeling to figure out what happened. So if we draw on hydrogens, it can help us identify what things have changed. When we go through and take a look at that top example, you'll notice that we have increased hydrogens through the course of the reaction. Okay? That increase in hydrogens may not have been obvious because we've implied the hydrogens. Okay, so in determining reduction and oxidation, it can be useful to go through and do that. Why is it useful to determine if we were reduction or oxidation? We now have an idea of a reagent. We need to be adding H2, okay, which is literally the reagent used for reduction. You can go back and take a look at your tables. Okay. If we go through and evaluate our definitions, though, I've only provided kind of half of them. So I'm going to expect you to kind of fill in the other half as we go through and do this. So let's move through the rest of our reactions. That very first one in the upper left, okay, or however you want to reference that, is an oxidation. And that, again, might be tricky to determine how it's an oxidation until you draw on your hydrogens. And when we go through and draw on the hydrogens, you should note that we have lost a hydrogen. Okay, so that is a decrease in hydrogen, which is going to suggest oxidation. The other thing that we can use to kind of help us through with that is that we've, increased the bonds to an electronegative element. We've exchanged hydrogen for chlorine. Chlorine being more electronegative than the hydrogen, that's an increase in electronegative bonds. That's oxidation. And the next one, you might be screaming, but hey, oxygen is more electronegative. Shouldn't that be an oxidation? Well, yes, but both chlorine and oxygen are more electronegative than the carbon, okay? Which means they were both already removing electrons from the carbon. They can't remove more because we haven't increased the number of bonds to those atoms, which means this is a neither reduction or oxidation. The other tip-off that we're looking at neither is that we could classify that reaction as a standard substitution or our SN mechanism. Yes, the first one could be a substitution, but we didn't talk about the exchange of a hydrogen because hydrogen's not a good leaving group. That's why we need different chemistry to come in, and that's why we're getting the oxidation. The next one down, if we go through and count our bonds to oxygen, we're starting with 3, we end with 2, which means we're doing a reduction. For those of you saying, but didn't I also decrease the bonds to oxygen because there's no longer an oxygen connected? Again, focus on where the primary chemistry is happening. The primary chemistry is happening at the carbon. Okay, that's my focal point. That oxygen that I just circled is not connected to the carbon, so I don't care about it. To our upper right, we're looking at oxidation. This is really just the inverse of what happened above, so that should be kind of your tip-off for that. Deciding how that happened, again, if we draw on our hydrogens, that can help us see that we lost hydrogens. We went from a total of 5 hydrogens to a total of 3. These 2 hydrogens were somehow removed from the structure. Okay. You might ask about, well, how did I increase bonds to electronegative atoms? Well, what's the difference between an sp2 carbon versus an sp3? Yes, we have actually increased bonds to electronegative atoms. The next one down, 1 bond to oxygen versus 2 bonds to oxygen. We're again referencing that as an oxidation. Okay. Again, you might be saying, but what about that hydrogen? Again, the hydrogen is irrelevant because it's not connected to the carbon. That hydrogen is irrelevant. The hydrogens connected down here are relevant because I have removed one of those hydrogens. And then the last one, same deal. We've increased bonds to oxygen. We started with 1 and we ended with 3. We also removed 2 bonds to hydrogen. Okay, so this next slide, well, hopefully everybody's good with that as I pause to ask if you have questions. I think genius. The next slide is our alkene oxidation reactions. and I'm actually going to pause the video and slide around so you can get the reduction in the same ones. So what we are starting with in this figure is we're starting in this center point, and each of these reagents branching out are our oxidation reagents. Okay? Some of them have extra rules that happen in secondary steps that are also oxidative or reductive. Even then, those phrases get a bit weird as far as labeling goes, because technically everything is oxidative on this slide. Okay? The secondary reactions for your epoxide are neither oxidation nor reduction, because we aren't changing the number of bonds to oxygen. All we're doing is adding a different oxygen or a new oxygen. So those are our big reactions for our oxidation. We will look through the details of those in theory in just a sec, or in the next video. But here I've got a pause so I can slide around and find our reduction reactions. Here are reduction reactions, slightly different format with a little bit more information than you saw in the past. And note the one thing in common for all of our reduction reagents, or nearly all of our reduction reagents, is the presence of H2. Okay, so hydrogen's being added in all of these. That last one doesn't have hydrogen, which is what makes it a good test question, because nobody knows what it does. Okay, so that's a good kind of flag question to memorize that reagent and how it reacts, because it doesn't fit the standard pattern of oxidation and reduction. And so with that, we'll go ahead and end this one, and we'll look at some of the details of those reactions in the subsequent videos.